Hello and welcome to another LeetCode video. Today we're going to be doing problem number 894, all possible full binary trees. And in this problem, you're given an integer n and you need to return the list of all possible full binary trees with n nodes. Each n node of the tree must have node value equals 0. Each element of the answer is the root node of one possible tree. You may return the final list of trees in any order. A full binary tree is a binary tree where each node has 0 or 2 children. So for this problem, we're actually not going to focus too hard on the examples because I feel like drawing out every single example is not going to be super easy. But we're going to more focus on the concepts of like what needs to happen. And so what needs to happen, we can write this down. So for our nodes, we need to do a couple things. So one, pick a root node, right? So let's say we have like 7 elements. We can say like element 2 is a root node or whatever. Then from there, divide up the rest into left and right subtrees. And then after that, get an array of trees for left and right, and then for every combination of left and right, make a new tree and add to result. Okay, so I'm going to show you more of that than like the actual what are all the combinations. So let's just say we have like 7 nodes, right? Let's go with 7 nodes. So let's do this. So let's say n equals 7. And we're going to just make roots here, and then we're going to figure out how to divide things. So let's say our root is going to be, by the way, let's think about one more thing. So for a tree, how many nodes does a tree have to be a complete tree, right? Like let's say we have 1 node. Can we make a complete tree? Well, yes, right? We can just have, like this is a complete tree. What about 2 nodes? So for 2 nodes, just to make a root node, a tree of 2 nodes, it would have to be like a root, and then it would have to be like another node. So this is not going to be a full tree ever, right? So what about for 3? For 3, yeah, we can have a complete tree, right? Like it is possible, or you know, a full tree. What about for 4? For 4, we're gonna have this. Then we're gonna have a left node. And now, how do we actually make a complete? There's no way to make a complete tree, right? Essentially, it's not gonna work. So we could do something like this, right? But now there is no right child here. We could do something like this, but now we need one more node somewhere. So you can kind of see that anytime n is even, so if n is even, we can't have a complete tree. So we can just throw those out faster to make like a simplification. Like if n is even, we're never going to have a complete tree. Well, what other base case can we run into? So another base case we can have, obviously, if n is 1, then we're obviously just going to have like 1 node, right? So that's going to be a base case essentially. And then there isn't base case if n equals 0, but we're not going to get to that. So technically, if n equals 0, we're not going to have anything either, but we're not going to get to that. So those are our 2 base cases here. But now let's actually figure out how do we divide this up and like how we would go through this quickly. Okay, so we know that we have to have at least 1 node in the left and the right? Because if n is even, we can't like if n is 7 and we just say like, okay, let's make the root 1, and then there's nothing on the left, right? There's 0 nodes here, and then there's 6 nodes on the right. Well, that's not going to be a full tree, right? There needs to be at least 1 node here and 1 node here, or none at all. So we're actually going to start counting n not at 1, but at 2, right? So we're going to say, let's make the root equal to 2. And now on the left, we have 1 node. And on the right, we have how many nodes? So we have 3, 4, 5, 6, and 7. So we have 5 nodes total, right? So we have 5 nodes total. And now this is doable to make a tree, right? Like something like this could be a tree. So there's 1 node on the left, and on the right, let's see, there's 1, 2. How would this work? So we basically have to make a 5-node tree here. So something like this could work. Right? Like this is a full tree, and there's 5 nodes here and 1 node here. So that works. But now that And basically what's going to happen here is we're going to have combinations here. So here we're going to have an array. So let's just say this is left, this is right. This is what we're going to recurse down, and we're going to have an array of all possible trees here. So with the left, there's obviously only one tree, right? It's just the root. And then with the right, there's going to be a bunch of trees. And we're just going to say for everything in the left and for everything in the right, let's make a new tree, right? Because if you have a list of possible left nodes and a list of possible right nodes, and all of them add up to 6, then you can just combine those to make all of your trees. But anyway, let's keep going. So what if we make the root 3? So if we make the root 3, then on the left we have 2 nodes, right? And then on the right we have 4, 5, 6, 7. So we have 4 nodes here still. This is always going to add up to 6, and we're just changing where our root is and then how many nodes are in the left and the right. So as you can see here, this is one of our cases that fails. So there's no need to make a left of 2 and a right of 4 because we know that we have to have an odd number. So we know that a root of 3 will fail. So we're not even going to go into that. What about a root of 4? Now we're going to have 3 nodes on the left, and then we are going to have 3 nodes on the right, and we'll have an array here and an array here. Well, that's going to work. What about a root of 5? So a root of 5 will have 4 nodes on the left and then 2 nodes. This is going to fail as well. So we're not going to even go into the 5. So we're going to go into 6. Now for 6, there's 5 nodes on the left, right? And 1 node on the right. And this is going to work as well. And so for each of these, what we need to do is this will be an array, this will be an array, these are all going to be arrays. And we're just going to say, okay, for each of these combinations, like this, we're going to say, okay, let's make a new root. And then for everything in left and everything in right? For all combinations, it's just like an nested for loop. For every single value in the left and every single value in the right, let's make that a tree. And that'll give you every single combination of every single tree you can have. So that's kind of what we're going to be doing, is we're going to be making these roots. And then what are going to be our values for the left and the right? So if this is like let's say we're just looping through something. Let's say we're looping through remember we need at least 1 node on the left. So let's say n is 7. Let's say we're looping from a range of 1 to n, and then we're actually gonna have a step of 2 here because, like I said, we never want an odd root, because an odd root means the thing on the left and the thing on the right is going to be even, or at least one of them is going to be even. Like if this was 8, and we'd have a root of 5, then we'd have 4 and 3. But either way, these have to be an odd number because you can't have a full tree with an even number. We established that. So in that case, what are we going to be doing? How are we going to have the left and how are we going to have the right? So the left is if we're just looping here, the left is actually going to be I, right? Because the first root is 2. So we're going to be looping here, and the first root is going to be 2. And so remember, this is 0 to n really when we're going to be doing a range. But yeah, essentially the left is going to be I, and the right is going to be n minus I minus 1, because that's how many nodes you have, right? So if you have 7 nodes, and this is going to be 0 indexed. So if our nodes are 0 to 6, for a number of 7, then if we're on 1, then the thing on the left is going to be 1, right? And then the thing on the right is going to be, how many nodes do we have left? Well, we have 5, right? So we have 7 minus 1 minus 1. Okay. Yeah. And then, so that's what's going to happen. And then we also have one other thing. And notice in this, the left and the right are the same, and in this, they're the same. So there is repeated work. So when we're generating all of these subtrees, we can do one extra step, and we can cache our results. So this is going to be kind of a dynamic programming problem, but I think the difficulty about this one is, like I said in my earlier video, you want to figure out the time and space complexity for your dynamic programming before you go that way. And for this one, the time and space complexity is really difficult and really not something you can figure out, because it's how do you know how many trees have, 5 or 20 or whatever? You can kind of go through your thought process of how long this will take, but it's kind of hard to come up with an exact solution of how many combinations are there unless you do combinatorics, as your job or something. Unless you're a mathematician, it's kind of difficult. And so I'll get into that later, and why I think that part of the problem is difficult, getting the space and time. But yeah, so let's go over what we have. So we need to pick a root node. We need to divide it up, And then we need to get an array of the trees of the left and the right. And then for every combination, we're going to make a new tree, add it to the result. Finally, we're going to turn in the result. And remember our base case is now, so if n is even, we're going to return an empty array because you can't have a full binary tree of an even when n is even. And then when n is 1, we're just going to return an array of a root node. And that's it. And then for any other end, we're going to do this left-right thing where we're alternating how many nodes are in the left and how many nodes are in the right. And we're going to use memoization to not do repeated work because, like I said, we're going to have a bunch of repeated work here. Because essentially what's going to happen is the left is going to start at 1 and will end at, n minus 2 and minus whatever. And then the right will start at a big number and will end at 1. So you're doing the same work multiple times. So we're going to get rid of that with memoization. All right, so I think we have enough to start coding now. So let's do that. And I think this problem is definitely not like super visually easy, but hopefully once we write the code, it's going to be a little bit more understandable. So we're going to have a visited for the memoization. And then we're just going to have like a tree generator or something, whatever we want to call it, right? So tree maker function. Okay. And we're going to take an n. And what are our base cases? So if n is 1, we're just going to return an array. We're going to return an array of a tree node. So it's just going to be a root node only, right? And all these values have to be 0 because that's what they stated in the input, right? So every single node has to have value 0. Okay, that's one base case. Now we have another base case. So if n mod 2 equals 0, remember we can't, this is a no solution. So we're going to return an empty array. Now the last one is if we have it cached, right? So if n in visited return visited n. Okay, and now we're going to have a result. And then we're going to do this loop that I was saying where we give some left and some right, and then we go through them all. So for I in range, remember, so you want to start at 1 because the left has to be at least one node. And then we're going to have a step of 2 because if you didn't have a step of 2, like if n was 2 and then there were 2 nodes on the left, that would never give you a valid tree. So we're going to have left equals tree maker of I, right? So this is going to go from 0 to n. So if n was 7, it would go from 0 to 6. So when it starts at 1, then left will have one node essentially. So left will have one node, and then it will just make this tree node here. So we're going to do this. Now the right, how many nodes are there left? So there are 7 nodes total. So it's going to be n minus the left, essentially, which is I, minus the root node, which is one node. Okay, so now that we have these arrays of left and right, this is going to be an array of, these are going to be arrays of trees that we can use for children. And now we just have to say, like, let's just get every single combination of left and right, and let's plop on a root in the middle. And that's going to be all of our trees with this kind of format, where there's one node and then there's 5 nodes here. And then we're going to do that for every single combination of nodes on the left and the right. So you can see in this example here, there's 1 node and 5 nodes, 1 node and 5 nodes, 3 and 3, and now there's 5 and 1, 5 and 1. But you could see that this is repeated work, right? Like this tree looks exactly like this tree and so on. And that's where we're going to do the memoization. Okay, so we're going to say for L in left and for R in right, we are going to make a root node. So we can say root equals tree node 0. And then finally, let's just make the left whatever the current left tree we're on is, and then let's make the right whatever the right tree we're on is. So we can say something like root.left, root.right equals left and right. And finally, let's append that tree to our results, and then let's actually cache it. So visited n equals result, and then we can return visited n. And then finally, we can call our function. So we can say return tree maker of whatever n is. So let's see how that goes. Okay, so we have this tree maker. Okay. So you can see it's quite efficient. I think when I ran it before, it was like 99% efficiency or something. But essentially, memoization adds a lot to the efficiency of it. So. But the thing I hate about this problem is remember when I said for memoization, like you always want to look into dynamic programming, but then it's kind of really hard to figure out like what's the runtime of this. Like, yes, we have n here, but how long does this take to run? Like, how many combinations are there? I think that part is going to be really difficult. And so essentially, I have to look this part up for the time and space complexity, but we can kind of go over it. So essentially, like let's say n is 7 here for this example, right? Like if n is 7, what are we actually doing for these combinations? Like how many combinations do we have? Well, it's going to be like, so if the left is 1, right? If the left has 1 value and the right has 5 values, that's going to be like a bunch of trees, right? Now we're going to have plus 3 and 3 like this, right? And then plus L5 times right 1. So this is essentially like what we're doing recursively, right? So if n is 7, first we're going to try the left with only 1 node, and then the right has 5 nodes, then the left and the right are 3, and then the left has 5 and the right has 1. So we're essentially doing this, and this is total trees for n equals 7. And then basically, if n is bigger than 7, what's going to happen is it's still going to go at 1 to 5, and it's not going to go 1 to 5. It's going to be more like I'm going to write it down here for just a generic n, right? So total trees for generic n value is going to be L of 1 times R of n minus 2 plus a bunch of stuff here, and then finally at the end it's going to be the reverse. So it'll be like L of n minus 2 times R of 1. But this is difficult. This is like not super easy to get, I guess. And so essentially what ends up happening here is this is a combinatoric problem in math. And so this actually ends up being, I think, n to the 2n over 2. Like this is what this comes down to as the number of combinatorics. And then I think it's that. And then also remember we also do this n times. So I think for every single number this will be this, assuming you can get these trees in constant time, which you should be able to, right? Because we're caching. But so I think it'll be something like this for the time. Like I said, I'm not entirely sure, and this wouldn't be something you would come up with on an interview. So I think it's called like the Catalan number if you want to look into it further. But yeah, it's going to be essentially like this, and then the space is going to be the same thing. Like the total number of things we can store is going to be like, we're going to have n number of, things in the visited, and then each array of trees is going to be this whole thing. So it'll be like n times this, essentially. Which, like I said, I don't think you can come up with it in an interview, but you can talk about like, okay, for every single one of these, this is how long it would take. This is roughly what we're doing. And then like, if you can't sum this up, if you don't know what the summation is for this, essentially, like, I don't think anyone's going to blame you. But yeah, so what I would say is, like, okay, so our visited has n items, and then this part obviously isn't linear time. There's going to be a bunch of stuff in here. So yeah. And yeah, that's going to be it for this problem. Like I said, I'm not a huge fan of the space and time. Honestly, I wouldn't even be, I think for this problem, you're not going to be expected to come up with it. I think if you just talk about it and like what you think will be pretty reasonable. So yeah, that's going to be it for this problem. Hopefully you liked it. And if you did, please like the video and subscribe to the channel. And I will see you in the next one. Thanks for watching.